Hello, good morning. Okay, we'll start. Okay, my screen visible? Hello. Yes, I'm audible. Hello.
Yes, sir.
Okay. Okay. So in last lecture we studied the ESDS encryption detail. So we continued with same example. Okay. So later we'll take the next part. So everyone try to focus on your slides. So the example of the ESDS encryption is very important. Okay. So we need to understood that how the cipher text can be generated from the plain text. Okay, so everyone try to focus on your screen. So we'll repeat the encryption process of the ESDS algorithm. Okay, so the ESDS nothing but the it is a part of DES algorithm that is called as a simplified DES encryption. Okay, so in SDS, so we have a first step as a initial permutation. Okay, so by using the particular beats we can first do the initial permutation on the plain text. So initial permutation means simply we have to rearrange the our plain text. So here we can represent the particular beats for yes ds of initial permutation, that is a 2 6 3 1 4 8 5 and 7. So after that, the second step is a expand and permutate. So by using these particular bits, that is a 4, 1, 2, 3, 2, 3, 4, 1, we can do the expand and permutate. Now how to do that thing? So for that we can take a one example. And the next thing is a permutate, that is called as a P4. So the bits are 2, 4 and 3, 1. Okay. So everyone focus on this example. Okay, so I will repeat this example for your more understanding. So the first step is a plain text. So here we have a plain text is of 8 bits. Okay, so on given plain text we have to do the initial permutation. So the initial permutation we have a particular sequence, that is a K2, K6, K3, K1, K4, K8, K5 and K7. So based on our plain text, so first we can mention the numbering for our plain text. So we can mention the numbering from 1 to 8 because our plain text is of 8 bits. So that's why we can mention the numbering as a up to 8. So based on the sequence of initial permutation, we have to rearrange the bit. So in our plain text, we can mention the number in a sequence that is from 1 to 8. So that's why in an initial permutation, we have to go with the keywords. So in an initial permutation, the first keyword is 2. So that's why we have to represent the second bit, a second position bit from our plain text. Okay, so anyone tell what is the second position bit in a plain text? Which one is the second bit in a plain text?
One.
Okay, so 1. Okay, so likewise, we have to mention the first initial permutation, that is a second bit, then K6, then K3, K1, K4, K8, K5 and K7. So with this sequence, we have to do the initial permutation on the plain text. So once we perform the initial permutation, so we have to split this initial permutation into two equal parts. So we have the initial permutation is of 8 bits. So we can divide these 8 bit into the two equal parts, that is a 4 bits and 4 bit. So we can divide this initial permutation into two equal parts. Okay, so one part consists of the 4 bits and other part also consists of the 4 bits. So based on this initial permutation, we have to perform the expand and permutate. Okay, so this expand and permutate operation we have to perform on initial permutation, not on a plain text. So for that, we can divide the initial permutation into two equal parts. Okay, so here we can provide the numbering as 1, 2, 3, 4 for the right side of the initial permutation. And based on the expand and permutate. Now here is the sequence of expand and permutate, that is a K4, K1, K2, K3, again K2, K3, K4 and K1. So first we have to write the K4 bit, then K1, then K2, then K3. Likewise, we can represent the expand and permutate. Okay, so have you understood the sequence of expand and permutate? Yes or no?
Yes, sir.
Okay, so once we perform the expand and permutate, so we have to use the key, and with the help of key we can perform the XOR operation. So here we have a 8-bit key. So based on the expand and permutate and key, we can do the XOR operation. So the truth table of XOR is, so when there is a same bit, the output is 0. When there is a opposite bit, output is 1. So likewise, we can perform the XOR operation on a expand and permutate and a key. So once we perform the XOR operation, we'll get the 8-bit output. So that 8-bit output we can consider as a S boxes. Okay, so left part we can mention as a S0 and right part we can mention the S1. So it consists of 8 bits. So we can divide the 8 bit into the two equal part, that is a 4 bit and 4 bit. So for one part we can call as S0 and for another part we can call S1. So once we get the S0 and S1, we have to represent the rows and columns. Now how to mention the rows and columns? So there is a one procedure to mention the rows and columns. So from S0 and S1, the first and fourth bit represents row, and the second and third bit represents column. So if we take the S0, so it is the first and fourth bit in S0. Yes, anyone?
00.
Okay. And second and third,
11.
one. Okay. So likewise, we can also represent as one bit also. So first and fourth bit in S1 is 0 and 1, that represents row, and second and third bit in S1 is 1 1, that represents column. So once we represent the rows and columns, we have to consider the binary representation. So the binary representation for 0 0 is 0, then for 1 1 3 in S1. So for 0 1 we can represent 1, and for again 1 1 we can represent 3. Okay, so once we represent the rows and columns, we have to consider the respective position for row and column. Now how to consider the respective position for row and column? So for that we have to consider the S box matrix. Okay, so in S0, okay, so we have to consider row and column. So in ES0 we can consider the row 0 and column 3. So we'll refer the matrix of ES0. Okay, so now anyone tell what is the uh, row 0 and column 3 in ES0? What is the position for row 0 and column 3 in ES0?
2.
2. Okay, so for 2, the representation is 1 0, and in S1 row 1 and column 3. So find out the position row 1 and column 3.
3.
3, very good. So we can represent the 1 and 1. So once we mention the ES0 and ES1, so we can combine these S0 and S1. So once we combine, so first we have to represent S0 and after that we have to represent S1. So it should be 1 0 1 1. Okay, so on this S0 and S1 we have to make the permutate operation, that is a P4. Okay, so for P4 the bits are K2, K4, K3 and K1. So for that we can mention the numbers for S0, S1 as a 1, 2, 3, 4. So we have to represent the sequence of a K4. So first we have to represent the K2, then K4, then K3 and then K1. Okay, so once we represent the P4, so again we have to perform the second XOR operation. So for second XOR operation we can use the initial permutation. So look at the output of initial permutation. So it is equally divided into the two parts. So first part is 1010. So we have to XOR our P4 with 10 and 10 and remaining bits, that is a 1001, we have to represent as it is. So once we perform the XOR operation, we'll get the certain output. So based on this output, we have to swap the bits. So left hand side bit goes to the right hand and right hand side bit goes to the left side. Okay, so this is our first step in a ESDS algorithm. So it is up to the swapping. So once we swap the things, so the half of the algorithm can be completed. So again, we have to perform the reverse procedure. Okay, so based on this, we can convert the plain text into the cipher text. Okay, so in this way, we can perform the encryption in a ESDS algorithm. Okay, so have you understood this example? Okay, so I hope you might be understood how to encrypt the plain text by using the ESDS algorithm. Okay, so now we'll move to the next part. Okay, so what we did in a ESDS, so simply we can represent the plain text, and based on the plain text we can use the key and we can generate the swapping function. So once we perform the XOR operation, so after second XOR operation we can swap the data. So if we swap the data, we'll convert our plain text into the cipher text. So again we have to convert the cipher text into the plain text also. So for that we can use the inverse initial permutation. Okay, so now we have to compare the two types of algorithm. So one is a DES algorithm and second one is a ESDS algorithm. Okay, so if we compare these two algorithm, so we can take the certain parameters. So the first parameter is a blocks. Okay, so it might be a we can how we can use the number of blocks. So in ESDS we can use 8-bit block, and in DS algorithm you can use 64-bit blocks. So second is a key. So in ESDS we can use 10-bit key, and in DS algorithm we can use 56-bit key. Okay, so based on the key, so in ESDS we can generate only 2 rounds, but in DS algorithm we can generate 16 round key. Okay, so next is a initial permutation. So likewise in an example also we observe that the initial permutation consists of 8 bits. So in a DS algorithm the initial permutation consists of 64 bits. Okay, so the ESDS or in a ESDS the function can operates on 4 bits, and in DS algorithm the function can operates on 32 bits. So in DS algorithm we have a two boxes and a two rounds. We can use S0 and S1 box for the ESDS, but for DS algorithm we have a total 8 yes boxes and 16 rounds. So based on certain parameter, we can compare the yes DS algorithm and DS algorithm. Okay, so in order to design the DS algorithm, we require the concept of S boxes. We require the concept of initial permutation. So based on the various design parameters, we can design the yes DS algorithm or DS algorithm. So along with the this DS algorithm, we can use more DS algorithm that is called as a multiple encryption with DES. So for multiple encryption, we have a multiple options, that is a double DES, triple DES with two key, or we can call as a triple DES with three keys. Okay, so in a single DS algorithm, we can use 64-bit key. So once we use the double DS, so 64 plus 64, we can use 112-bit key. And in a triple DS, we can use three keys, that is a 64 plus 64 plus 64, that will be 168-bit key. Okay, so simply double encryption means we have to perform the encryption into two two times. So first we can do the encryption by using the key 1. So same encryption we have to perform by using the key 2. So that way we can secure our data. Okay, so instead of one time we can perform the encryption two times. That's why it can called as a double DES. So we can generate the ciphertext from the plain text by using the encryption technique, and we can recover our plain text from the ciphertext by using the decryption technique. And in a triple DES, so there are the two types of triple DES. One is a two keys and another is a three keys. So by using the triple DS, so we can use the three keys at a one time. So three keys for encryption as well as three keys for decryption. Okay, so by using this type of encryption, we can also secure our data. So these are the multiple encryption details of the DS algorithm. So it called as a double DS and triple DS. Okay, so in a DS algorithm, we can study certain things. There is a first is a block cipher and a stream cipher. Then we can study the design principle of Fiestel cipher, and we can study the DS algorithm in a detail, and the multiple encryptions of DS. There is a double DS and triple DS. Okay, so these are the details of DS algorithm. So the DS is the most important part from the block ciphers. Okay, so here we complete the part of a DS. Okay, so there is a one more part from the second unit, so that will take in a next lecture. Okay. Okay, so next part is a concept of divisibility. So it is a concept of mathematical modeling. So that thing we'll take in a next lecture. Okay. Okay. So today we'll stop here. We'll take this part in evening lecture. Okay. So you can put your numbers in a proper sequence, and then you can left. As only 16s are present. Just put your numbers in a sequence. Okay, so once we put your number, you can left. The remaining part will continue in our next lecture.